This illustration shows the complete anatomy of an inflatable packer, broken into all functional layers. At the center is the mandrel, the rigid steel backbone that carries tensile and compressive loads from the workstring. Around the mandrel sits the inflation chamber, which receives hydraulic pressure from tubing, coiled tubing, or wireline setting tools. The inflation chamber is protected by reinforcing braid made of Kevlar, steel wire, or composite fibers. Elastomer layers chosen for well temperature, chemistry, and pressure. Anti-extrusion rings that prevent the packer element from squeezing into casing imperfections. Ribs or metal fingers for anchoring type systems. Once pressure enters the chamber, the membrane expands outward, forming a high contact area seal against casing or open hole. This cross-sectional view helps engineers understand how structural integrity is maintained despite extreme expansion ratios. Inflation mechanism and flow path. This illustration explains how pressure actually inflates the packer. When setting pressure is applied at the surface. 1. Fluid travels down the tubing or CT. 2. It enters the inflation port aligned with the packer's hydraulic chamber. 3. A check valve ensures one-way flow. Once pressure enters the chamber, it cannot escape. 4. Pressure builds inside the expandable membrane. 5. The membrane begins to outwardly expand. 6. The elastomeric layers stretch while reinforced braided layers control the shape and prevent overexpansion. This mechanism is critical for live well operations and deviated wells, where mechanical manipulation is limited. It also highlights why clean fluid and no debris are essential to avoid blocking the inflation pathway. Expansion ratio, collapsed versus inflated. Inflatable packers can expand 1.5 times to 3 times their run-in hole diameter, far beyond any mechanical packer. This illustration compares collapsed mode RIH, small OD for navigating restrictions, smooth outer surface, element tightly folded against mandrel, inflated mode, big OD that conforms to casing or open hole, high radial force sealing against irregularities, ability to seal damaged casing or large washouts. This visual emphasizes why inflatable packers are used when conventional packers cannot seal due to washed-out formations, irregular boreholes, elliptical casing, large variations in ID. It clarifies the engineering principle. Inflation gives conformity, not rigidity. Setting mechanisms comparison. This illustration compares 3 distinct inflatable packer activation methods. 1. Hydraulic set. Uses tubing or CT pressure to fill the inflation chamber. Ideal for horizontal wells because it does not require pipe movement. 2. Wireline set. A wireline tool applies pressure using a small hydraulic pump. Critical for slim holes, live wells, deep multi-zone testing. 3. Chemical activated. Self-inflating fluid reacts and expands over time. Used in abandonment operations. Long-term zonal isolation. The illustration helps the viewer understand which setting method to choose based on well geometry, pressure limits, and operational constraints. Cased hole versus open hole applications. This illustration explains the versatility of inflatable packers. In cased hole, the casing ID is smooth. Expansion is uniform. Seal reliability is predictable. Used for cement squeeze, pressure tests, or temporary abandonment. In open hole, the formation may be irregular. Washouts, cracks, and cavities are common. Inflatable packers naturally conform to rough surfaces. Ideal for isolating intervals during formation testing or stimulation. This technical demonstration clarifies why inflatable packers are uniquely suited for uneven geometries where mechanical packers fail. Failure modes. This illustration shows realistic field failure modes that cause inflatable packers to lose integrity. Elastomer tearing occurs when overinflated or exposed to sharp rock edges. Debris preventing expansion. Scale, sand, or cutting stuck behind the element cause incomplete inflation. Thermal degradation. High temperature causes elastomer hardening, shrinkage, or blistering. Valve leakage. Loss of inflation pressure leads to collapse under differential pressure. Slippage occurs in extremely soft formations where inflation force cannot anchor. This visual acts as a troubleshooting guide for supervisors and workover engineers to diagnose packer integrity issues. Field operation, Straddle isolation system. This illustration demonstrates a straddle assembly, the most common field use of inflatable packers. Two inflatable packers are spaced apart on the mandrel, upper packer, lower packer. When both are inflated, they create a sealed interval between them. This system allows acid stimulation, water shutoff, zonal isolation, testing individual layers. The illustration shows pressure arrows entering the isolated zone, demonstrating how fluids are directed precisely where needed. It explains why inflatable packers are essential for old wells with damaged casing, open hole production tests, multi-zone intervention, thief zone isolation,